Hello, and welcome to Enabling the Third Wireless Revolution, Transformative RF and Millimeter Wave Circuits, Wireless Systems, and Sensing Paradigms with Professor Harish Krishnaswamy. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by the MTTS Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so that you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the slide area. You can also go into full screen mode if you desire. Refresh or reload the current page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now, let's introduce our speaker. Professor Harish Krishnaswamy received the B.Tech degree in electrical engineering from IIT Madras in 2001 and the MS and PhD degrees in electrical engineering from the University of Southern California in 2003 and 2009, respectively. In 2009, he joined the electrical engineering department at Columbia University in New York, where he is currently an associate professor and the director of the Cosmic Laboratory. In 2017, he co-founded Mixcom Incorporated, a venture-backed startup to commercialize Cosmic Laboratories' advanced wireless research. His current research interests include integrated devices, circuits, and systems for a variety of RF, millimeter wave, and submillimeter wave applications. Professor Krishnaswamy is the recipient of numerous awards, and he has been a member of the Technical Program Committee of multiple conferences. Currently serves as a distinguished lecturer for IEEE Solid State Circuit Society and as a member of the DARPA Microelectronics Exploratory Council. Now it's my pleasure to turn the virtual podium over to Professor Harish Krishnaswamy for Enabling the Third Wireless Revolution, Transformative RF and Millimeter Wave Circuits, Wireless Systems, and Sensing Paradigms. Harish?
Thanks, Mike, and thank you to everyone who's tuning into this webinar, and good morning, good afternoon, or good evening, wherever you are in the world. So this is the outline from my presentation. I'll talk about what I call the third wireless revolution, and I'll specifically focus on what the hardware challenges are to enable that, and then I'll delve deeper into some hardware design challenges associated with millimeter wave circuit design, full duplex wireless, and massive MIMO wireless. And I'll obviously focus on work that's happened within my research group at Columbia University towards these new wireless communication paradigms. And then I'll conclude the presentation with a few comments on future research directions that are needed to enable this third wireless revolution. So on this slide here, I'm essentially summarizing global handset data traffic as it has evolved over the last several years. And what I'd really like to motivate with this slide is that we're really living in the era of big data, obviously, but wireless is a big part of the big data revolution. So, wireless communications is a critical piece as to how we move large amounts of data around these days. And as you can see, over the last several years, we've been seeing a doubling of the total amount of data that's been being moved around wirelessly, to the point where now in 2017, or in the year that just passed, over 20,000 petabytes of data were moved wirelessly to handset devices. And this is really being driven by the fact that smartphones and tablets have sort of replaced the personal computer as our computing devices of choice, and we're now using these devices for applications such as streaming video and web browsing, as opposed to just making calls or texting. And I think if you look back at wireless over the last 20, 30 years or so, you can really break up the developments of wireless into three different revolutions, so to speak. So the 1990s were an era where cell phones really became prominent for the first time, and what cell phones enabled was the ability to immediately communicate with anybody across the world. And this revolution, this communication revolution, was essentially sort of contemporaneous with the widespread deployment of both 1G and 2G wireless technologies. Then when you look at the 2000s and the 2010s, the decades that we're in right now, the wireless revolution that wireless revolution enabled us to have immediate access to massive amounts of data at our fingertips. So wireless connectivity got good enough where on our handset devices, we were immediately connected to the internet no matter where we were, and you'd have access to any amount of information via the internet. So I really think of this as a wireless data revolution. Now, the question is, what will the next generation of wireless technologies bring to us? So what will this third wireless revolution enable? So we're really talking about, to some degree, 5G and, of course, 6 and 7G when they come about. So what will these enable for us? So what I envision is that these wireless revolutions will enable us to be connected to the physical world in new ways. So when you think about the internet, obviously there's a very large amount of data available on the internet, but it still pales in comparison to the information that's actually contained in the physical world, in the geometry of it, in the material properties of it, etc. And what I really envision the third wireless revolution will enable is for us to be able to interface with this physical world and to be able to interrogate it and interact with it in fundamentally new ways. So this includes wireless delivery of 3D video for virtual and augmented reality. It includes wireless paradigms for gesture recognition, vision quality, RF to terahertz imaging, so RF to terahertz imaging with extremely high resolution, vision quality resolution, the ability to sense the composition and the material properties of the objects around us, etc. And so this is really what I think the third wireless revolution will be about. Now, enabling this third wireless revolution, we have started to look into new paradigms for wireless. And some of these new paradigms are summarized here. So on the top left, you have the use of millimeter wave spectrum, which is an order of magnitude higher than what we have historically used in the RF. On the top right, you have full duplex wireless, which is the ability to transmit and receive at the same time at the same frequency. And then you have massive MIMO on the bottom left. And then you have spatial modulation on the bottom right, which is still something that's in the more theoretical domain and hasn't really been reduced to practice as of yet. So, there's new ways of wireless communications that are becoming prominent as a part of this next wireless revolution. And if you think about 5G as the first the first generation of that next wireless revolution, we're really looking to these new wireless paradigms to deliver a 1000x increase in data capacity compared to existing wireless technologies. And we've also started to see activity in big companies, in major companies, towards the new applications that would be enabled by wireless. So on the top left, we have the SOLI project from Google, which is really using 60 gigahertz radar for gesture recognition. Both Google and Facebook have active efforts on using millimeter wave technology, specifically 60 gigahertz again, for delivery of internet to underserved populations, as well as essentially to form ad hoc backhaul networks for the next generation of wireless. So we're really seeing major companies embrace these new wireless communication paradigms, as well as build new applications on top of wireless. So, it's certainly exciting, but I think there are several technical challenges to overcome. And one important technical challenge is this trade-off between spectral efficiency and energy efficiency. So certainly as we look towards things like full duplex and massive MIMO, we're trying to push the efficiency with which we use wireless spectrum. But historically, spectral efficiency is always traded off with energy efficiency. So there's an open question as to whether in delivering these higher data rates, we can actually do so with a reasonable energy consumption that essentially doesn't break the bank compared to what we're doing today. So is it possible to achieve very high spectral efficiency through techniques such as MIMO and full duplex while still maintaining the extremely energy efficient nature of much simpler systems? And in order to be able to do this, I would argue that, when we, as hardware people, when we think about how we build radios, we really need to rethink the way in which we architect radios today. So on this slide, I'm summarizing the traditional architecture of a radio, which has historically been broken into 4 different domains: the front-end domain, the RF, the analog, and the digital. and each of these domains has a different toolbox associated with it. For instance, in the front end, we typically use electromagnetics and acoustics to design antennas and filters. In the RF, this is really high-frequency circuit design. In the analog, this is now more analog, complex circuits. And then certainly in the digital domain, that's where we really get to very high levels of circuit complexity to perform very advanced signal processing functions. What I'd like to argue is that to enable these new wireless paradigms, we really need to rethink this architecture of the radio. And specifically, we need to think about how we can move functionalities that were traditionally implemented in one domain into another domain. So for instance, there's been a lot of interest in software-defined radio, essentially flexible radios that can work at any frequency across a range of spectrum. And that has really pushed research on how we can achieve channel select filtering, which has typically been done in the analog domain, up in the RF and even at the antenna interface. And there's been a lot of work in the circuits community on the so-called end-path filters, which are tunable, high-quality filters that you can implement on a chip that essentially give you this channel select filtering in the analog domain. And I would argue from these new wireless paradigms, we need to even go one step beyond that. We need to start thinking about how we can embed more complex signal processing functionality that has traditionally been implemented even in the digital domain up in the RF and even in the antenna. So can we think about doing signal processing at the RF and even potentially at the antenna to enable these very challenging wireless communication paradigms? So with that, let me jump into some of the research that we have been pursuing along this direction in each of these emerging wireless communication paradigms. So first millimeter wave, then full duplex, and then massive MIMO. So the millimeter wave spectrum is, certainly it's generated a lot of hype recently with, the interest from 5G. So, loosely defined, it extends from 30 gigahertz to 300 gigahertz. And the promise of millimeter wave is that there's very wide bandwidth available to do very high data rate communication. But there's also a significant challenge associated with millimeter wave. And I would argue that the most significant problem with working at the millimeter waves is that as you go towards higher frequencies, the power that you can generate from any electronic device or circuit goes down. It actually goes down with a 1 over F or 1 over frequency rate. And so that's sort of what's captured on this chart where I'm plotting saturated output power of power amplifiers implemented in different silicon technologies versus the frequency of operation. And so while certainly at low RF frequencies at 1 or 2 gigahertz, you can implement power amplifiers with a watt of output power, as you get up into the millimeter wave frequency range, you're typically talking about 10, 20, 30 milliwatts of output power, or 10 to 15 dBm, so to speak. Aside from output power, the efficiency of a power amplifier is also fundamentally challenged. So while at lower RF frequencies, you can get efficiencies that are in the high 40, 50, 60% range in silicon CMOS, at millimeter wave frequencies, efficiencies are typically in the 15 to 20% range because of increased losses in both your active and passive devices. And so this really makes millimeter wave communications challenging because you cannot generate power, you cannot transmit the signal very far, and because the efficiency is low, the battery drain would also be quite significant. So we've been working on efficient, high-power generation at millimeter wave frequencies in silicon-based technologies, and we've particularly been looking into this idea of device stacking. The main problem at millimeter wave is that to work at these high frequencies, you need to use a very scaled CMOS technology node, and associated with that scaled node is a very low supply voltage or a low breakdown voltage. But the idea in device stacking is that while a single device can handle a relatively low voltage, a stack of devices can handle a linearly larger voltage. So their voltages can essentially add up the stack. And so if you use a stack of n devices, you could increase the output voltage by a factor of n, and hence increase the output power by n squared, because power is proportional to square voltage. So you can get quadratic increases in output power as you stack more devices. And this is a technique that particularly SOI, silicon on insulator CMOS, allows you to do, because as you stack devices while the gate, drain, and source voltages add up, in a bulk CMOS technology, the bulk voltage would still remain fixed and would limit your breakdown. But in silicon on insulator, you can essentially float the body or the bulk of the device, thus allowing essentially the voltages to freely float up the stack and reach very high levels. So, the idea sounds fairly straightforward. Of course, getting something like this to work at millimeter wave involves a lot of circuit design challenges. So how do you tune the amplifier correctly so that all the voltages add up? So I'm not going to go into all those details because this webinar is really going to focus on just giving a high-level description of the ongoing research in different wireless communication paradigms. I'll show you some references later on that you can read for additional details on how to design stacked power amplifiers. Here I just want to summarize the kind of performance that we have seen. So what this allows you to do is in SOI CMOS at millimeter wave frequencies, we've been able to get output power levels in the 17 to 23 dBm range, so 50 to 200 milliwatts with efficiencies as high as 35%. So this is a good 10 dB or 10x higher output power than what you can get using conventional PA design and bulk CMOS. We've also looked at low-loss power combining approaches. So we've looked at power combiners that can allow you to combine up to 8 power amplifiers with high combining efficiencies as high as 75%, which, given the limited back end of the line available in CMOS, is quite high. And with this, we were able to combine 8 of these stacked PAs and actually show a power amplifier with nearly a watt of output power. So it had a saturated output power of half a watt at millimeter wave frequencies, which still is, this work has been about 3-4 years old now, but it's still the highest output power reported in a silicon CMOS millimeter wave PA. So as promised, that's just an overview of the millimeter wave power amplifier work. Certainly there's a lot of ongoing research on how to improve power and efficiency outside of my group as well as other research groups across the world. These are just some references from my research group on these ideas of device stacking and low-loss power combining to get high output power and high efficiency. So with that, let me move on to the next wireless paradigm that's of interest, so full duplex wireless. Conventional wireless circuit design is half duplex. In other words, the transmitter and the receiver either work in different time slots, which is called time division duplex, or they work in different frequencies at the same time, which is called frequency division duplex. The idea in full duplex is if you can transmit and receive at the same time at the same frequency, then you can potentially double your network capacity immediately in the physical layer. And there are certainly many other benefits associated with being able to do this at higher layers of the network stack. So it has the potential to significantly improve network performance. And while in the wireless community we call this full duplex, often in other communities this will be called simultaneous transmit and receive, or STAR. The big channel associated with the full duplex is if you're trying to listen at the same time at which you're transmitting and at the same frequency, then you will hear a tremendous interference from your transmitter, which cannot be filtered away because it's at the same frequency. And this transmitter power can be significantly more than 100 dB more powerful than the weak desired signal that you're trying to receive. And so, the only way to get rid of it is to do a cancellation because it's technically a signal that you know. So essentially you need to do more than 100 dB of what's called self-interference cancellation to cancel out this echo from the transmitter so that you can receive your weak desired signal. And because you need more than 100 dB of cancellation, there's no way that you can do it in a single stage. No single stage can be that precise to give you 100 dB. So you have to do it at the antenna, then again at RF, then again in the analog, and again in the digital. And if you get sort of 30 dB from each of these stages, then the overall cancellation can be in the vicinity of 100 dB to 120 dB. And, that's not the extent of the challenge. So 100 dB of self-interference cancellation already sounds pretty high, but there are other challenges associated with it as well. So the challenge is that the self-interference channel from the transmitter to the receiver can be pretty frequency selective. So the signal that leaks to the receiver doesn't actually look exactly like your transmitter signal, but it will be distorted in frequency because there is a certain amplitude response and a certain phase response and a group delay in the signal getting from the transmitter to the receiver, whether it's through a direct leakage between antennas or after reflections from the environment. And so on this slide, what we've done here is that we've basically taken the measured self-interference channel from a pair of antennas and then simulated the type of cancellation that we can get with a simple canceller across the bandwidth of the signal. And so what you can see here is that as the bandwidth of the signal increases, the cancellation can become pretty small. So if you want 30 dB cancellation, the signal bandwidth has to be 2.5 to 3 megahertz. As the bandwidth becomes 10, 20 megahertz, the amount of cancellation is pretty small. It can be as small as 10, 15 dB. And so just kind of looking at this a little bit more to understand why this happens, the issue is that on the graphs on the right, the self-interference channel, which is shown in red, changes with frequency, but the most simple canceller, which taps the signal from the transmitter, adjusts the amplitude and phase and injects it into the receiver, is flat with respect to frequency. And so while you can get them to exactly match each other at one frequency, as you move away from that frequency, they will deviate from each other. And so while at that frequency you can get a pretty deep cancellation notch, as is shown in the bottom graph, as you move away from that frequency, the cancellation becomes worse, to the point where at the extremities you can actually be worsening the problem. You're not even just doing cancellation, you're actually increasing the level of self-interference. So how can we solve this problem? Well, you can essentially think of this as a filter design problem. The self-interference channel has a certain filtering profile. You want to replicate that filter within your canceller so that they exactly track each other in frequency. And so what folks have looked at, this is work from Stanford University. They were among the first groups to demonstrate full duplex at the system level. And so what they essentially did is that in their canceller, they effectively built an RF FIR filter. So they essentially have multiple delays on a board implemented using microstrips and a different attenuation on each of those delays. And by varying the attenuation on each of those delays, you can essentially create a sort of FIR filter in the RF. And by adjusting those delays, you can create an arbitrary filter profile to match your antenna interface. The challenge is that if your antenna interface has delays of 8, 9, 10, tens of nanoseconds, the delays that you implement on the board in the form of a transmission line will become extremely long. So, a microstrip with 10 nanoseconds delay on a typical PC board can be 20 centimeters long. So there's no way that this would fit in a small form factor device. So we looked at how we can actually build these kinds of equalizing cancellers on a silicon chip. And so we looked at doing this in the frequency domain. So if I have a reprogrammable second-order bandpass filter that I can put in the canceller, then now my canceller has 4 degrees of freedom: magnitude, phase, but also the center frequency of the bandpass filter and its quality factor. And with these 4 degrees of freedom, I can match not only the magnitude and phase of the self-interference channel, but also their slopes. So you can see here that I'm showing these green graphs which represent the canceller transfer function, and they have second-order profiles which have been drawn to match not just the amplitude and phase, but also their slopes across frequency. And so then when you do the cancellation, you get a much more wideband cancellation profile because you're emulating the channel over a wide frequency range and not just at a single point. So we're essentially replicating not just the amplitude and the phase, but also their slopes. And we know that slope of phase is essentially group delay. So what these filters are doing is creating group delay to match the channel. And then we can take it one step further, where if I have multiple taps like this, each with a separate programmable bandpass filter, then I can emulate the magnitude and phase as well as their slopes at multiple frequency points, basically in different subbands, and start to get very wideband cancellation profiles. So now you can see that I can get these cancellation profiles here at the bottom right graph, where you have multiple notches and essentially a very wideband suppression of the self-interference. Essentially what we're doing here is equalization of the self-interference channel for cancellation in the frequency domain. So we call this frequency domain equalization. Now, obviously, this technique works in the signal processing type of way of looking at it, which is what I've shown here. The question is, can we build these filters on chip? Because even time domain equalization works. It's just that there was no way to build such large delays on a chip in a reasonable form factor. But this is where there's been some major advances in the RFIC community. So in the RFIC community, people have really made a lot of progress on these so-called NPAT filters, which are essentially switched capacitor filters where the clock signal is being run at an RF frequency. And so if you have a set of switches, capacitors, and another set of switches with the switches being run with non-overlapping clocks at an RF frequency, then one can show that this switched capacitor circuit has a second-order bandpass transfer function, which can have a very high Q, and that Q is essentially dependent on the capacitor value. So we can have now filters whose quality factor can be programmed just by changing these capacitors. What's more, you can also include active GM cells in a ring configuration as shown here in blue in the switched capacitor filter, and essentially make them switched capacitor or switched GMC filter, so to speak. And by changing the GM value, we can even change the center frequency of the bandpass filter, which normally would have been at the clock frequency, but now can shift relative to the clock frequency based on the GM value. So I can program Q and I can program frequency. I can also change the load and source impedance of the filter, so I can program the magnitude response. And what my group particularly has shown is that if you phase shift the clocks on the right-hand side with respect to the clocks on the left-hand side, you can program the phase shift of the filter as well. So now we have a programmable filter where you can change its quality factor, center frequency, magnitude, and phase. So this is all that you need for a single tap of this frequency domain equalization canceller. So based on this idea, we built a 65 nanometer CMOS full duplex receiver at about 1 gigahertz with this with 2 taps of this frequency domain equalization canceller. So we have 2 filters here. And this is what the chip photo looks like. Obviously, these filters still occupy a significant amount of area, but they're still quite compact compared to an onboard transmission line to get the same amount of delay, which would be 10 to 20 centimeters long. And based on the chip, we did some measurements across a pair of antennas as a self-interference channel, which has 8 nanoseconds group delay. What we showed is that when you do a regular cancellation, you get that red curve, which is very narrow band. But then when you engage this frequency domain equalization canceller with 2 taps, you get the blue curve, which is significantly more wideband. It has about 25 megahertz cancellation bandwidth, which is 8 times more wideband than the conventional canceller shown in red. So this frequency domain equalization idea really pushes the bandwidth over which you can get a cancellation. And so we've done demonstrations of this with actual modulated waveforms. We've shown that for a 27 megahertz modulated 64 QAM waveform, this canceller can suppress that self-interference over its entire bandwidth by as much as 20 dB because of the frequency domain equalization. So that was our first work into getting wideband cancellation. The next generation of work that we did took this into the antenna domain. So in the antenna domain, polarization is another degree of freedom which we can use to get isolation. So if you use orthogonal polarizations for transmit and receive, then you can increase the nominal isolation from something like 15 dB for these co-located slot loop antennas on a PC board to something like 25 dB or so if they're using orthogonal polarization. So that's a nice little increase in isolation that you get from polarization, but it's obviously not a huge step towards getting 100 dB of cancellation. But what we found is that in the polarization domain, we can even embed cancellation. So the way we do it is the following. So you have these 2 antennas, one for transmit and one for receive, that are using orthogonal polarizations. But on the receive antenna, we introduce another port which is co-polarized with the transmitter port. So now what happens is, while there's a direct path from the transmitter to the receiver, there's also this indirect path where some signal couples from the transmitter to the receiver to the copolarized port. And there we terminated with a reflective termination so that it reflects the signal back into the antenna so that it couples to the receiver port. So we've now created a second indirect path. And by playing around with this reflective termination, we can choose its value such that this indirect path perfectly cancels the direct path to get cancellation at your receiver input. So it's a polarization-based antenna cancellation. And now that we're doing this, we can use these same filter design ideas in the design of this reflective termination. So we can actually calculate the impedance that is required in the reflective termination to get cancellation over a wide frequency range, and then we can look to synthesize that impedance by using higher order networks in this reflective termination. And so in our first work, we just used actually a second order network, an inductor, a variable capacitor as a diode, and a variable resistor using a transistor, and that's already enough degrees of freedom to get a cancellation with extremely wide bandwidth. We show that you can get as much as 450 megahertz bandwidth cancellation, where the isolation is better than 15 dB. So, we're getting extremely wide cancellation right inside the antenna by essentially doing frequency domain wireless channel equalization inside the antenna itself. So we first built this at 5 gigahertz and tested it, and we were able to show, again, 50 dB isolation. That's this black curve over 300 megahertz bandwidth. The interesting thing is this is now programmable because that reflective termination can be made variable. So what we showed is that if you bring a metal foil near the antenna, that can mess up the cancellation and you get this pink curve, but then you can reprogram the reflective termination and you can get back this green curve, which is as good as the black curve originally was. So it's not only very wideband cancellation, but it's also programmable to combat changes in the electromagnetic environment. And then we went up to 60 gigahertz and implemented at millimeter wave frequencies as well, where you have exactly the same slot loop antennas implemented on a PC board, and they are interfaced with a chip, and the reflective termination that programs the cancellation is actually on the silicon chip. So this is the architecture of the silicon chip. It's a 60 gigahertz direct conversion transceiver, but the main thing is that it integrates the reflective termination to control the antenna cancellation, and it also includes a second RF cancellation that just adjusts the amplitude and the phase. So those are the circuits that are shown in red. So this is the first implementation of a full duplex transceiver at millimeter wave frequencies, and we did extensive measurements with it. We actually showed the ability to have a millimeter wave link running at roughly about a meter of distance, where in the absence of the cancellation, the signal at the receiver is completely dominated by this 1 gigabits per second BPSK signal, which the chip is transmitting. But once you engage the antenna and the RF cancellation and the digital cancellation, we can suppress the self-interference, which is this BPSK signal, and receive a sine wave that is being transmitted from about a meter away from a discrete transmitter with the same output power as the chip. So we're actually able to get about 7 dB of signal to interference plus noise ratio in a link at about a meter distance at millimeter wave frequencies with this antenna cancellation. So that's some of the work that we've done on wideband cancellation. There's another challenge with full duplex as well, which is how do you design the antenna interface for full duplex? Obviously, you can use 2 antennas, but that's undesirable because, if you have 2 antennas, you might want to use those 2 antennas for MIMO or for other ways to increase capacity. So there's really an interest in using a common antenna for full duplex. But then when we look at how we can connect a transmitter and receiver to a common antenna, if we design a 3-port network that is matched and reciprocal, then any 3-port network that's matched and reciprocal and cannot be matched, reciprocal, and lossless at the same time. So any reciprocal network that connects a transmitter and receiver to an antenna and is matched will have at least 3 dB loss. So the question is, how can we avoid this 3 dB loss in the antenna interface for a single antenna? Well, the answer is you have to build non-reciprocal circuits. So you have to build things like circulators, which can route the signal in a rotational fashion without any loss. So fundamentally, any linear time-invariant passive network based on traditional materials is reciprocal. In order to break reciprocity and build circulators, we have to break one of these conditions. So you can use non-conventional materials such as ferrite materials, but those cannot be integrated in silicon, and they render the component bulky and expensive. So there's an interest in doing things on a silicon chip so that it can be low cost and small form factor. You can violate linearity and make nonlinear systems, but fundamentally any wireless system needs to be linear, so this doesn't really work for any wireless radio. You can violate the passive condition and use active transistors, which are inherently non-reciprocal, but active transistors add noise and add distortion. So that brings us to the the final condition that can be violated, which is time invariance. Can we make a circuit time variant and hence non-reciprocal to enable circulators? And this is an area where there's been a lot of research interest over the last 2 or 3 years or so. So we have been looking at how we can build time-varying circuits that are non-reciprocal. And so on the left, what I show is how magnetic circulators work, which is based on Faraday rotation, where if you take a ferrite material and apply a magnetic field, then for waves traveling in the direction of the magnetic field, the polarization rotates in one direction, but for waves traveling in the opposite direction, the polarization vector rotates in the other direction. So essentially, this magnetic field twists the wave in different directions for waves traveling in opposite directions. What we're trying to do is use high-speed switches to create the same kind of a twist. So what I show on the right-hand side is sort of a cartoon representation where we have a switch that is rotating on one side and then a bank of media, which are shown with these brown bars, and then a switch rotating on the other side as well. And what I show in the middle cartoon is the switch on the right is leading by 90 degrees compared to the switch on the left. And so now what happens when you do this is for a wave traveling from left to right, it sort of gets twisted in the counterclockwise direction because it first sees the lagging switch and then it sees the leading switch, and that gives us a plus 90 degree phase shift, while a wave traveling from right to left sees an opposite twist in the clockwise direction, and that gives it a minus 90 degree phase shift. So this phase shifted switching gives you a non-reciprocal phase shift. Now, that's sort of like a mechanical cartoon representation. How would I implement this in a circuit? So this comes back to end-pass filters. So I'd build the same switches, capacitors, and switches. But now what I would do is I would give a phase shift to the switch on the right-hand side so that now if I travel from left to right, I get the same end-pass filter response, but I get a phase shift in one direction. But for signal traveling from right to left, the magnitude response is still reciprocal, but I get a phase shift in the opposite direction. So I get a non-reciprocal phase shift in this end-pass switch filter just by delaying the switches on the right-hand side. So now with this non-reciprocal phase shift, how can I make a circulator? So I take an end-pass filter with plus minus 90 degrees non-reciprocal phase shift, and I put a 3 lambda by 4 transmission line around it. And so now if I think about a wave that's traveling in the clockwise direction, it starts from one end. When it reaches the other end, it picks up minus 270 degrees phase shift. Then it picks up the 90 degrees phase shift, the minus 90 degrees phase shift of the end-pass filter. And so it gets minus 360 degree phase shift, and so it essentially ends up at the same place where it started. So you can have wave propagation clockwise. But in the counterclockwise direction, it'll pick up minus 270 degrees from the line, but plus 90 degrees from the end-pass filter, and so that's minus 180 degrees, so it's out of phase from where it started. So this prevents wave propagation in the counterclockwise direction. So this non-reciprocal phase is allowing me to create a ring in which signals can only rotate in one direction, and that's essentially what a circulator is. So then I can add 3 ports on this ring and essentially realize an ideal circulator. So, you can do the analysis of this time-variant microwave network, and what you find is you get exactly the S parameters of an ideal circulator. And all you need is switches, capacitors, and a 3/4 of a wave transmission line. So we built this on chip, this in 65 nanometer CMOS at 750 megahertz. So this was the first passive circulator on a chip that doesn't use any magnetic materials. And it's also significantly compact, almost 25 times smaller than a comparable circulator implemented using ferrite devices because it's being miniaturized on a silicon chip. So you can take a look at this reference to see additional details. Just to give you a sense of the performance that we're able to achieve, so we can get low loss, 1.7 dB loss. So we're beating the 3 dB fundamental loss limit of reciprocal networks. And the isolation can be quite high. At a single frequency point, you can get as high as 50 dB isolation. Of course, what you really care about is the bandwidth of the isolation. And I think for this work, the 20 dB isolation bandwidth is about 32 megahertz or 4%. So you can get low loss and strong isolation, albeit in this particular implementation over fairly narrow bandwidth. We followed up on this. This was our first chip-scale circulator. It was, I guess it's about 2 years old at this point. We've done several follow-up works on this. So we integrated the circulator with a full duplex receiver on the top left. On the top right, we figured out a way in which we can combine a circulator and a receiver into one circuit, and that improves all performance metrics of it. It improves the noise figure, improves the transmitter power handling, reduces the power consumption. On the bottom left, we've also shown how you can go up to millimeter wave frequencies. So we showed a circulator at 25 gigahertz intended for 5G applications. It used a switched transmission line architecture as opposed to a switched capacitor architecture, which also makes it more wideband. And then more recently, this is unpublished work that will be at the Radio Frequency IC Symposium in Philadelphia in June. We showed how you can make circulators at 1 gigahertz with very high power handling. They can handle 1 watt of transmitter power. So there's been quite a bit of progress on this particular work. Again, I would direct you to these references to read more about the circulator as well as our full duplex work more broadly. So, we're coming to the end. In the last 10 minutes or so, I'm just going to talk a little bit about massive MIMO and then conclude the presentation. So there's a lot of interest in massive MIMO. It's really expected to be a significant part of 5G. Virtually every major wireless company is looking into it. The idea in MIMO in general is you can use multiple antennas to send multiple data streams, which you would disentangle on the receiver side using MIMO signal processing. So in general, if you have N antennas, you can send N independent data streams and increase the data capacity by a factor of N. Typically, MIMO receivers are built using what's called the digital MIMO architecture, where you have N generic receivers and you digitize all of them. And then in the digital domain, you can do all the MIMO signal processing. So you can form multiple simultaneous beams. You can do complex space-time array processing, which is really the basis for MIMO. Another benefit of having an all-digital receiver, as this is called, where every element is digitized, is you can even do digital array calibration. The challenge with this all-digital architecture, where you have no spatial processing in the analog domain prior to the A to D, is that all the RF and analog portions are exposed to any blocker signal that you have. So you need very high dynamic range in the receivers in the analog to digital converter. So what we've been looking into is how we can, in the analog and RF, do some kind of preliminary spatial processing where you can have a single notch so that in one angle of arrival direction, you have a notch which can suppress the signal, but all other angles of arrival are passed so that you can then digitize all elements and do your MIMO digital signal processing. That was our first work. And in the second work, we extended this to arbitrary spatial filtering, where you can have an arbitrary number of notches so that you can suppress interferers, multiple interferers coming from different directions, but all other directions are passed for digitization so that in the digital domain, you can do MIMO digital signal processing. And so the idea is that these approaches would kill your blockers before you get to the A to D, so they would reduce the dynamic range requirement of the analog to digital converter, which is really the dominant factor in these types of MIMO receivers. So this is the first work. We showed how you can get a notch in one direction. So what I'm showing here on the right-hand side is a two-dimensional conversion gain graph, where on one axis I'm plotting the gain versus frequency, but on this other axis I'm plotting the gain versus angle of arrival. And so across frequency, you get the traditional band pass response that any receiver will give you, but along the angle of arrival axis, you get a notch at one angle of arrival, which here is set to 0 degrees. And then our generation 2 prototype, we extended it to be able to form multiple simultaneous notches at arbitrary locations. And so these are some measurements of the conversion gain versus angle of incidence, where I'm showing the ability to form multiple notches simultaneously, and these notches can also be individually steered or individually programmed. So each of these prototypes was 4-element MIMO receivers, and working in the 1 to 3 gigahertz frequency, or 0.1 to 3 gigahertz frequency range, but the ability to form these notches and steer these notches in any direction. So again, I'm not going into the details of how we do this. again, I would direct you to some of these references here that talk about the circuit techniques that you can use to do this kind of spatial filtering. So that's a little bit of our work in the MIMO area. So hopefully what I've shown you is new circuit techniques that give you better output power, reduced interference, and so on and so forth in the millimeter wave frequency range, as well as for new wireless communication paradigms such as full duplex and MIMO. And certainly we've looked at how we can combine these. So we've seen how you can do full duplex at millimeter wave, for instance, and build circulators at millimeter wave. We have ongoing work on how to do MIMO at millimeter wave as well. So that brings me to the conclusion. So I'd like to really look forward, to the future with this concluding slide. What are the other things that need to get done to enable this third wireless revolution? So we need advancements to be able to, to be able to use really high millimeter wave spectrum to do extremely wideband communications, as well as to do things like MIMO and full duplex. We need advances on all fronts, on the devices side, on the circuit side, and in the system side. On the devices side, we really need advancements in device technology. So this would include things like gallium arsenide, indium phosphide, gallium nitride, et cetera, to really push the Johnson limit. So to push frequency of operation as well as power handling. But also we need techniques to integrate these emerging devices or these more exotic devices with CMOS, which will always be the workhorse for signal processing and circuit complexity. So heterogeneous integration technologies are required. On the circuit domain, we really need advancements in circuits that allow us to do things like synchronization and timekeeping across the network. So what I've shown in this presentation is ways to make a single radio better, interference cancellation, higher output power, things like that. But how can we now have multiple radios in a network communicating with each other such that they improve the collective network performance? And this will really require advances in synchronization of radios across large distances. And then finally, at the systems level, again, things at the network level are very important. So there will be a large amount of data that is shuttled and collected and shuttled across networks when we're using very large bandwidths at very high frequencies. So ways in which we can prune down this data to get the information contained in it. So things like compressive sensing, but at the network level, feature extraction, those things become very important. And all of this needs to be done while thinking not just about capacity of the network, but also the latency of the network and the reliability of the network. So, that brings me to the end of the presentation. And I think we're just about out of time here as well. So thank you very much for your attention. And I'm happy to take any questions that you might have at this time.
Awesome. Thank you, Harish. That's fantastic. This is a great presentation. And you're getting several bravos and great presentations here from the Q&A submissions as well. So now it is time for our question and answer session. So we've got a few questions here right now, but before we start that, just remember that you can also continue to submit your questions through the Q&A panel. Okay, so there are a few questions here. I'll try to kind of combine these. And I think you touched on it just a little bit, but maybe there's some additional comments that you can make. So, for example, what other comments could you make about, say, for example, the heterogeneous integration, silicon carbide, gallium nitride, gallium arsenide, et cetera?
Yeah, absolutely. So, I think, there's a comment here that we're talking mainly about CMOS PAs. So what about other 3.5 technologies, and how do you do heterogeneous integration? So the reason I spoke mainly about 3.5 PAs is twofold. CMOS PAs is twofold. One is that's my area of research. So I'm primarily a CMOS RFIC person. And so that's what I've looked into in detail. Also, as we go towards millimeter wave frequencies, people are thinking about using large arrays with thousands of elements, and it becomes challenging to integrate that level of complexity using a pure 3.5 process. So heterogeneous integration is actually very important. So there are many ways in which you can do heterogeneous integration. So there are efforts to actually grow 3.5 materials on silicon So there's active research going on in that direction. I think of Professor Mark Rodwell at the University of California, Santa Barbara is doing excellent work along those lines. So that's one approach, which is probably more future-looking. Some of the more near-term ways that people are thinking about doing this is sort of die-level integration. So can I 3D integrate little dielets of 3,5 PAs, whether they're in gallium nitride or indium phosphide or gallium arsenide, on top of a CMOS chip. And so this really requires things like through silicon vias or through substrate vias and die-attach techniques. And so the questions are the things that people are working towards is how compact or short can we make these interconnects? Can they be low loss enough? Can they be well controlled enough? Can they be well matched enough? Especially if we're putting hundreds of 3,5 dies on a large CMOS carrier chip. So those are all ongoing research directions on this heterogeneous integration direction.
Yeah, that's great. And I think you touched on one of the other questions here, too, which was how are these circuits interconnected? And I think you already answered that with TSVs, flip chips, et cetera. That's a very ripe area for research. Let's see here. So we'll stay on this topic of SOI transistors. Do you have any comments on how you handle timing issues, phase jitter, et cetera, in the RF front end at millimeter wave frequencies?
Yeah, so at least my interpretation of this question is it's sort of alluding to the hysteresis effect that SOI transistors have, which is the body is not contacted, and so the threshold voltage can sort of float and drift over time, and it shows you can have a history-dependent threshold voltage effect. So what we found is that, at any reasonable or RF or millimeter wave frequency, the signal is so fast that you don't really see a significant hysteresis effect. And so, for the RF circuits themselves, if you're thinking about an LNA or a power amplifier or phase shifter, there doesn't seem to be a significant hysteresis induced effect in those types of circuits. I think in the analog baseband circuits, that's where you see them a lot more. So in the mixed signal circuits in the baseband, ADCs, samplers, those kinds of things, people do worry about the hysteresis effect of SOI CMOS. And so what people tend to do there is, the modern SOI CMOS processes from Global Foundries, for instance, which is the one that we use extensively, they also offer body contacted devices. So where you do actually get a contact to the body and you can force the body voltage. Of course, that device will be a little slower because there's more parasitics associated with the body contact. And so there is a little bit of a speed price to be paid there, but that is basically the transistor that people will often use in the mixed signal circuit design to basically counter the hysteresis effect associated with the threshold voltage and its impact on things like timing, jitter, et cetera.
Got it. Okay. Let's see here. Do the benefits of MIMO at lower cellular frequencies, for example, with dispersive propagation, translate to millimeter wave where transmission is line of sight based?
Yeah, so that's a very good question. So, MIMO at millimeter wave will look very different from low frequency MIMO. So, so when people talk about massive MIMO, they're really thinking about sub-6 gigahertz, where, the base station can have a very large number of antennas, and you can essentially do MIMO across that large number of antennas. There's also multi-user MIMO, where you're using the large number of antennas to communicate with multiple users. Each user, though, is still a single antenna system. At millimeter wave frequencies, you're absolutely right that reflections are weak, and the channel is very large. It's highly line of sight, so that you don't have a large number of reflections that are giving you a truly a multipath within channel. So there, what people think about for MIMO is to do sort of line of sight MIMO, also known as spatial multiplexing, where you basically are just forming multiple beams, and then each of these beams are spatially separated enough from each other that there's little beam-to-beam interference, and then you're putting independent data streams on the independent beams. And so people think about these for backhaul networks, where you have a large number of antennas at the in between two backhaul at two backhaul nodes, and you're using line of sight spatial multiplexing at millimeter wave to get very high data rates. So so there you have to the challenges you have to counter are different. So there for line-of-sight spatial multiplexing MIMO, you have to meet the Rayleigh criterion, and so you have to think about what the inter-antenna spacing is for those beams to be separate enough from each other.
Okay, great. And just to note, there's still a few minutes here to get your questions in, so if you have questions, feel free to go ahead and submit those. Okay, so we've got another one here. It says, from the perspective of 3GPP standards, is there an effort to include full duplex wireless capability in 5G specifications?
Yeah, so I mean, I think 5G, so there are people who are certainly trying. So, you know, you have startup companies that are working towards this. So, you know, there's Kumu Networks, and there's some others as well. There's a tech company in Texas that's looking to use full duplex for 5G. I think, you know, whether full duplex makes it or not into 5G for the traditional application of doubling the data capacity by using the same spectrum for both transmit and receive, I mean, it's an open question, and I think there are challenges there. One is that, you know, it starts to require sort of like an infrastructural overhaul because, you know, all the bands that we've been traditionally using for TDD and FDD have to suddenly be changed, and that will require massive changes to the infrastructure that exists. But, you know, it can be useful in other ways beyond your traditional access to the handheld device and doubling capacity of that access link. So, for instance, you can use full duplex to make repeaters, which would be used to extend the range of a wireless link. And so people are looking to do this. So relays or full duplex relays or repeaters, for instance, for backhaul networks is one possible application of full duplex. So, you know, I think you might see full duplex making its way into 5G, but for things other than the doubling of data capacity. And I would also mention that aside from 5G and wireless, there's a lot of interest now in full duplex for wireline communication. So, for instance, you know, DOCSIS, you know, doing bidirectional transmit and receive or full duplex transmit and receive in DOCSIS type applications is drawing a lot of interest as well.
Okay, great. And maybe we'll call this the last question here. So in the systems you're talking about, what kind of effective number of bits do you have for the ADCs and DACs?
Yeah, it's an excellent question. You know, let me focus a little bit on millimeter wave here because I think that's where, you know, the ADC and the DAC becomes a huge problem. So because, you know, aside from the number of bits, the sampling rate at millimeter wave frequencies is very high because we're trying to use very wide bandwidth. So I think it's still an open question. So typically, you know, I think the typical number people think about, let's say 8 bits of resolution, you know, in a millimeter wave ADC. You know, it's basically what you need for, you know, with some margin for the most complex constellation that people might actually want to use. People are considering 256 QAM for 5G. So, you know, you need some resolution for that. But I think there's a lot of interest. There's active work going on how you can manage with low resolution analog to digital converters. So you'll find theoretical papers out there on how to do millimeter wave with even 1-bit ADCs, or, you know, at least with low resolution ADCs. And, you know, some of the insight behind trying to use low resolution ADCs for millimeter wave is that we're using a large array for millimeter wave typically. And in an array, even the ADC quantization noise sort of gets suppressed after array combining. It can be an uncorrelated noise across the different channels, which gets suppressed when you do digital beamforming. So there's some sense that there might be ways to get away with lower resolution in large arrays. But, I mean, I think it's still an open question.
Excellent. Okay, well, thank you very much for answering all those questions. There are still a few here in the queue, but unfortunately we are out of time, and I believe the presenter will follow up with those unanswered questions offline. So as we said earlier, this session will be archived on the Society website at mtt.org. All registrants will get an email reminder with a website address when it's available. For attendees that would like to receive PDH credits, please follow the link that's in the webcast view and also use the code that's provided on the last slide of this presentation, which is being shown right now. Once again, I'd like to thank Professor Krishnaswamy for this excellent and informative presentation. Special thanks to our audience today for joining us, and we hope that you found today's event valuable and that you'll return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a great day.
Thank you very much. Bye.